Welcome again to the Digital System Design course. In last lecture, we have discussed introduction about the Digital System Design course, why it is beneficial for the undergraduate engineering students, and then why digital systems are taking 360-degree application, find 360-degree applications in all day-to-day life and other areas of applications. Then the first very topic we have discussed in the last lecture was introduction to various number systems. In that one, we discussed with conventional decimal number system. Then we also introduced binary number system, and then two other number systems we discussed as hexadecimal number system and octal number system. Now in this lecture, we shall discuss how a particular number from one number system can be converted to another number system. This is going to be useful when we are dealing with the different numbers given in different base systems. So this lecture is going to be dedicated with the number base conversion. Again, what we are going to discuss is a number given in a particular base, how that particular number can be converted in an equivalent number in another base. First, we are going to discuss from any base to the decimal. That means any particular number is given, and we are going to discuss in how this particular number can be converted into decimal number system. So very general number we have taken on a particular any general base. That's a number is xyz and base is p, that's radix is p. So what is the procedure is a particular number when expanded on its base, that means this xyz with its position values are there. Z has a position value of 0, y has a position value of 1, x has a position value of 2. Where I am going to expand this xyz on the given base p, the number automatically converts into decimal number system. That means end result will be in decimal number system. This is how it is going to be expanded. X multiplied by p power 2 plus y multiplied by p power 1 plus z multiplied by p power 0, and the end result will be answer in decimal number system. So the one line is when we want to convert a given number from its given base to decimal number system, we just have to expand the number on its given base, and the answer will be and resultant number will be in the decimal number system. These are the examples. First one, we have a number 127.4 base 8. It's an octal number. Number constituents you can easily find out that they are varying from 0 to 7. And this is hexadecimal numbers. This is given in base 16. So number constituents are 0 to 9, then A to F, what we have discussed in earlier lecture. So we want to convert these two numbers in decimal number system. So what we will do, we will just expand these numbers, that 127.4 base 8 and B65F base 16 on this number on base 8 and this number on base 16. This is how it will look. You can easily figure out the position values. Here it's a 0, it's 1, it's a 2, and this is for minus 1 base position values. And here it's a 0, 1, 2 and 3. Okay. So I am going to expand this particular number like this one, 1 into 8 power 2 plus 2 into 8 power 1 plus 7 into 8 power 0 plus 4 into 8 power minus 1, and the number 87.5 is equivalent number in decimal number system for the given number 127.4 in octal number system. Similarly, for the second number, that's a hexadecimal number B65F base 16, we all know that B is 11, 6 or 5 and F is 15. So this is 15, this is 11. So 11 into 16 power 3 plus 6 into 16 power 2 plus 5 into 16 power 1 plus 15 into 16 power 0, and the resultant number 46687 will be in decimal number system. So takeaway from this particular slide is given number in a particular base, when we are going to expand that number on its given base, resultant number will be in decimal number system. Now the next one we are going to discuss is decimal to other base. That means a number is given in a decimal number system and we want to convert into any other base. So the first number, the procedure will be, we have to here take note of the given number may have integer part and some fractional part also, like 23.14. So this is a decimal number. It has a integer part also and a fractional part also. Please note that there are different methods to convert integer part into destination number system, and another method is for fractional part. So we will implement individually. First we are going to discuss the integer part, then we shall discuss the fractional part also. So for the integer part, what is the rule is repeated division and remainders generated by each division. That means this is the number given in decimal number system. This number shall be divided with the destination base. That means the number in which we are going to convert the given number. So we are going to divide this xyz with the p, and then this process of division is going to be repetitive, and the remainders we are going to segregate from down to up, bottom to up, and that will be the answer. So for example, we have a number x41 given in the decimal number system, as was the objective was decimal to any other base, and we want to convert that particular number into binary number system. So the question is 41 base 10, and you have to find out what will be the equivalent number in binary number system. This is the problem. So how we will deal this particular one? 41, what we have said that it should be divided with the destination base or radix. So we will divide this 41 using 2, divisor here, remainder here, again divided by 2, divisor here, remainder here, again divided by 2. We will repeat this particular process until we got the result 0, and then all the remainders we are going to write down in reverse order: 101,001, 101,001. This is the equivalent number of 41 base 10 and this 101,001 in the binary. So these are the equivalent numbers. We have converted the integer part. Next we shall discuss the fractional part, but for the integer part, repetitive divisions and remainders generated by each division we kept in the answer in reverse order. Now second example is 153 base 10, as the number is given in decimal number system. We have to convert this number in octal number system. So the problems may look like this one: 153 base 10, and we have to convert a number, find out the number having base 8. So what we shall do? Obviously we are going to divide 153 by 8, okay, and we are going to write down the divisor and then the remainders here: 8, 2, then 3, then 8, it's a 0 times, then 2. So the number what we got is 231 base 8. You can easily also check the answer or verify the answer whether the answer is good or not. In the last conversion we have learned that any number when expanded on its given base, it is going to convert into the decimal number system. So if I am going to convert this answer, I am going to check the correctness of the answer. So I am going to expand this particular number. So 2 into 8 power 2 plus 3 into 8 power 1 plus 1 into 8 power 0. Once you will calculate, you will get 153, and the rule was when we are going to expand the given number on its base, the number shall be converted into its decimal number system. So this was the part for integer part. Now for the fractional part, what we have to do, earlier for the integer part we have done the repetitive divisions and we take care of the remainders. Here we are going to follow the process of repeated multiplications, and in such a way that either all fractional part becomes 0 or we got some significant numbers. So fractional part is multiplied by p, that means destination base, to give an integer and a fraction. Again the same fraction is multiplied by again to give a new integer and new fraction. This process is continued until the fraction becomes 0 or until the number of digits had sufficient accuracy. We will learn using these examples. So the example is 0.6875. 0.6875 is the number. Obviously the number is given in the decimal number system and we have to convert into binary number system. So the process is, this fractional part must be multiplied with 2, that's a destination base, that's a radix number, and the answer we will get this one in the first step of multiplication. Now we will again take this fractional part 0.3750, again multiply, we will get this number. Again we shall take this 0.7500, again multiply with this one, we will get this one, and then 0.5000 multiplied by 2, fractional part becomes 0 and the answer will be 1011 in the top down manner. So the answer will be, since radix part was there, 0 point, so 0 point and 1011. So the answer is 1011. Look here. Okay. The next number is 0.513 base 10 and we have to convert this number into octal number system. So again the same fractional we have taken 0.513. Please note that here the whole fractional part becomes 0, but here it may not be. So we are going to repeat the process up to 5-6 steps for the significant accuracy. You need not worry to make this fractional part necessarily 0. 4 5s or up to 6 steps, you will get the approximate answer that is going to be assumed as a correct answer only. So 0.513 is the number. We are going to multiply with 8. Why 8? Because that's the destination base. In that octal number system we have to convert this number. We got the number 4.104. Again we will take the fractional part 0.104 multiplied by 8. We got 0.832. We will again take this one, multiply by 8 and repeat the process up to 4-5 steps, and that's the answer, 406517. So again fractional part will be there because that was there in the original number. So 0.406517 base 8. You can also write like this one, 0.406517. That's up to significant bits, it's a correct answer. So for any base to decimal, just expand the number, and for any base to decimal, for integer we have to do the repetitive division, and for the fractional part we have to do the repetitive multiplications. Now some examples in which both parts are going to be covered, that means integer plus fractional part. So in this particular number is in decimal number system 27.3145 base 10, and we have to convert this number into binary number system. So we have identified that this part is integer one, this part is a fractional one. So integer part we are going to divide, repetitive division, and in fractional part we are going to do the multiplication part. Destination base is binary only, so we are going to divide in the to convert the integer part, and we are going to multiply with the 2 in converting the fractional part. So 27 divided by 2 subdivisor part, remainder, again 13 divided by 2 we got 6, remainder 1, again 6 divided by 2 we got 3, remainder is 0, again 3 divided by 2 we got divisor 1, remainder 1, again 0 times, and we got this one, and this all is going to be written down in this approach. So we will get 11011. So 11011, this is the part from the integer part. And and on the other hand side, for the fractional part we know that we have to multiply. So 0.315 multiplied by 2 we got 0.630. We will again multiply this fractional part with 2, we got this one. We have to take this part only. So 0.260 again 2, we got 0.520, 0.520 again multiplied by 2, we got 1.040. Although again please note that this part doesn't become 0, but 4-5 steps it will give the right answer. So this came from this part and this particular came from this particular part, 0.0101. So we got the full answer for the integer part as well as for the fractional part. Next one is we are going to convert binary, octal and hexadecimal in this particular manner. Suppose a number is given as binary, we can convert into octal, or again octal to binary, and similarly binary to hexadecimal and hexadecimal to binary, and also octal number to hexadecimal and hexadecimal to octal. This is the thing we can convert. So before delving into this particular topic, we should keep in mind that there is a definite relationship between these three number systems. You have noted in first lecture that binary, octal and hexadecimal. Binary has a base of radix of 2, octal has a base of radix of 8 and hexadecimal has a base of radix of 16. That means this is related with 2 power 3, 2 power 3 is equal to 8 and this is related as 2 power 4, that is a 16. That means there is a definite pattern which is going to be applicable in the octal and hexadecimal number systems when compared with the binary. So binary to octal and binary to hexadecimal. Suppose a number is given 11011. This is a binary number. I am going to convert into octal or hexadecimal. As you know that this is 2 and this is 8. This one is 8. So combining 3 bits of binary is going to result in the octal number system. On the other hand, combining 4 bits of binary number is going to resultant in the hexadecimal number. This is the plain rule. But please note that if decimal point is there like 110 like this one, so we should start from decimal point in this direction and from decimal point in this direction. You please note this particular point while converting the number from binary to hexadecimal and binary to octal. So the rule is it can be done partitioning the binary number into groups of 3 digits each, because binary to octal, starting from the binary point. I am talking this one as a binary point. This one is the binary point. So start from here, that means in this direction and in this direction. To the left and to the right. To the left and to the right. Conversion from binary to hexadecimal is similar, but now this time it's a 2 power 4, that means 4 bits, group of 4 bits. So this is the number we are going to convert into a octal number system here, and here it's a hexadecimal number system. So please note that this one in octal, so we will start from this is the decimal point or radix point, and this number is going to convert into octal number system. So we will start with the taking group of 3 digits, 3 digits, and this is 2 only, so we may add 0. Similarly, this is in the left direction, left one, and now in the right. So considering the reference as a radix point, 3, then 3, then 3, then 3. Okay, and with the table only I can figure out which number is this one. Similarly, for the hexadecimal number system, taking reference of a radix point, 4 numbers, 4 digits again, and this is again 4. Add zeros. You can add zeros. 4, 4. That's done. So this is how binary number can be converted into octal and binary number can be converted into hexadecimal. Look, the same example. For more clarity, I have highlighted the points, digits, and similar equivalent digit in the octal number system again. So 011, the number is 3, you can easily figure out. 101, number is 5, 001, number is 1, then 110, it's a 6, and then 010, that means its number is 2. And similarly, 111 is going to be 7, and similar for the other digits. And similarly, in the binary to hexadecimal conversion, it's a 1011, then this one, then this one, and then. So look at this number, it's a 10 and then 11. B is 11. So this number is 11. You can easily figure out this one also how it's going to be 11. This is binary number 2. So it's a 0, 1, 2, 3. If I'm going to expand this number, 1 into 2 power 3 plus 0 plus 1 into 2 power 1 plus 1 into 2 power 0. Look, 8 plus 2 plus 1. Number becomes 11. So in hexadecimal, the number is B. Okay. This is how you can convert a given number from binary to octal and hexadecimal number systems. Then octal to binary and hexadecimal to binary, that's a reverse. Conversion from octal or hexadecimal to binary is done by reversing the procedure, what we have done earlier. So 3-digit binary equivalent, each octal 2 power 3 is equal to 8. So that's the equivalent. And similarly, each hexadecimal digit is converted to 4-digit binary number. So simply we can write down what is the equivalent number. So this is 16, that's a hexadecimal number. I am going to convert into binary number system. So each digit of this particular one is going to be converted into 4 bits equivalent in binary, and here 3 bits. So look, 6 is going to be represented by 0110, 4 is going to be represented by 0100, C 10, 11, 12. So it's a 1100, and D, that's a 13. So 1101. But here only we require 3 digits to represent, because number is in octal number system, number is going to limited at 7 only, and for these all numbers to represent 3 bits of binary is going to be sufficient. So it's a 0. Look at the difference. 2 is going to be replaced by 010 in binary. 6 110. Look here, 6 is going to be represented by 4 digits, same only 0110, but that's a 4 digits, and here it's a 3 digits only. Numbers are same only, but here to represent all 16 we need 4 bits, but here 3 bits are sufficient to represent 2 010 and 4 100. This is how we can convert a number from octal to binary and hexadecimal to binary. This is the end of the lecture 2. A lot of other numericals we can do based on the conversion of number systems from one base to another base. Thank you.